My name is Azalea Shillington, and this was my research project on variability in black holes. This was directed by postdoc Deepika Bollimpalli. Okay, a little about me. I'm from Cincinnati, Ohio. I'm a high school senior. I'm a huge astronomy nerd. I'm also a huge robotics nerd. This is my robotics team here. In fact, I have two brothers, one not adopted and one adopted. So the goals of this project were to investigate variability features in black holes, specifically in accretion disks, and find out what affects that variability. And we did this specifically through the power spectra. This kind of research is super important because for the smaller black holes, the stellar mass black holes, we can't simply just take a picture of them. So these variability features and these characteristics that affect these variability features are super important when we're modeling these black holes so we can connect the dots and figure out how these black holes proceed and how they behave. So a background, first of all, both of the simulations I used were X-ray binaries. And the characteristic of these is that they both have a companion star. So this companion star accretes matter directly into the accretion disk, which is a super hot, dense disk of gas that orbits very, very rapidly around the black hole. As you get further and further into the black hole, you reach the event horizon, which is the specific point at which light can no longer escape the black hole. So it's where the black hole gets black. And then in the very center of mass, we have the theorized point of singularity, where it's infinite density. But unfortunately, accretion disks aren't that simple. So on here, we have an accretion disk. In the center, we have the inner accretion flow, which is kind of like a donut shape. It's less dense, but super hot and very pressurized and very magnetic, and it goes super rapidly. We also have the outer accretion disk, which is more flappy, it's more flat, it's more dense, and it's a little bit colder, but it's still super hot, and it goes a little bit slower. Okay, another thing that we're looking for when looking for this variability is quasi-periodic oscillations. So this is like a specific characteristic of oscillations that we find with objects that emit X-ray light, specifically in X-ray binaries. These are super important because we see them as a specific feature in accretion disks, and that helps us to model that variability when we're modeling our simulations. So here's a simulation that I used. I used two of them. We can see the inner torus here and here, and we can also see the outer accretion disk here. So both of my simulations had a spin of 0.9. And in black holes, they have spins from -1 to +1. And that tells you how rapidly they're spinning and then in what direction they're spinning. So these simulations were spinning super duper rapidly. Also, the difference between these two simulations is that in the first one, the black hole spin axis was misaligned with the accretion spin axis by 15 degrees. And the second one, they were perfectly aligned. Okay, so at first, we first modeled time, radius, and accretion rate. And the way you read this, we have time on the y, radius on the x, everything's in gravitational units. The way you read this, for example, at radius 100, you see it goes pink, which means it's emitting matter, and then blue, which means it's accreting matter. So we see that it goes pink and blue, or pink and white, or blue and white, or blue and white. So we know that there's some frequency at which it's taking in matter and then letting out matter. And what we're looking for is that specific frequency. So we can do this through the Fourier transform, which is a little bit complicated. But basically, when you have a bunch of signals and then you have a mixed signal, it comes out as the integral of all those signals. And then we can dissolve this back into those individual frequencies through the Fourier transform. And from the Fourier transform, we can go the time space from the frequency space. And with the frequency space, we have frequency on the x and then power on the y. So, for example, we can see at these specific frequencies, the power is super high. So then we're able to dissolve it back into those original waves that make up that big wave up there. When I did this, I did a Fourier transform for every single radius. So the way you read this, you have radius on the x, frequency on the y, and then power as the contour. So for example, at radius 100, you have a frequency of around 0.005. Or at radius 10, you have a frequency around 0.04. And one specific feature we notice is how it gets kind of horizontal lines as we get more and more closer to the center. And that's because we enter the torus, and everything in the torus rotates pretty in sync. Versus as when we're out here, all the outer accretion disk oscillates as on its own local frequency. And those local frequencies are characteristic of specific mathematical models for black holes. So we have the Keplerian frequency, the vertical epicyclic frequency, and the radial epicyclic frequency. If you notice, in all of these, we have this A value, and that A value is the spin, as I said before, is 0.9. So we know that as our spin changes, these characteristic frequencies change. So on the other hand, if we know these characteristic frequencies, then we know the spin of the black hole, which is super important when we're modeling black holes. So that brings me to the other variables we analyzed. First of all, we have the theta velocity, which is when it goes up and down. This also corresponds to the vertical epicyclic frequency. We have the accretion rate, which is the rate that matter enters and exits a specific radii per unit of time. Radial velocity, which is how close it is to the center of mass, and this also corresponds to the radial epicyclic frequency. And then the phi velocity, which is how fast it's orbiting, which also corresponds to the Keplerian velocity. Another feature we noticed was that at some points there were multiple strong powers, and we wanted to see if this was a transient feature or a persistent feature. Okay, so through here we did a dynamic power spectrum where each plot is for just one radius. So we have time on the x, frequency on the y, and power as the contour. And for example, at radius 2, we see that the power is highest around 0.025 per like 10,000. And then as we move on, it's always persistent at 0.04,000. But as we get closer here, there's another one at 0.02, which is really interesting. And we're not sure why, but we know later in the simulation that the accretion disk started orbiting around a different axis, which is an odd behavior. But what's cool about my research is that I went to time 50,000 versus the paper that my research was based off of only went to time 25,000. So these patterns can be observed in other variables as well. And here we have the time space on the left, power space on the right, average theta velocity on the top, radial velocity on the bottom. And you can see that we also have the slide feature and the horizontal lines feature. This, how it gets blurry here, is actually an artifact of the specific code I was using. But one interesting thing in this radial velocity, you can notice that there is not any pink, which means that it never goes backwards, which means that since the spin is so high, it always stays in one persistent. It's always going faster, it's always going around in one direction, but sometimes it's slowing down and going faster and slowing down and going faster. So all of these past graphs were used for the 15-degree tail. But when we compare it to the 0-degree tail, we see that these features are nowhere near as persistent. So we can say that with a 15-degree tilt, or the more misaligned your axes are, the more QPO variability we'll have. Oh, okay. Okay. And then the last thing we did was magnetism. This is a power spectrum. We have the power on the y, frequency on the x, and then each individual line is a specific specific radius. And my mentor and I couldn't find anything significant about this graph, but it was just cool to show and cool to look at. Okay, so to conclude, variability is super important when we're trying to model these smaller black holes. Again, because we can't take a picture of them. And we found that QPO features were found in the torus or corona region, but they weren't really as present in the outer floppier regions, and those oscillated at their local frequencies. And then misalignment, so the misalignment between the spin axis and the black hole spin axis and the accretion disk spin axis, the more it's misaligned, the more QPO features and the more variability we see.